Dear students, welcome to the sixth and final lecture of limit and continuity. So today in this talk we shall discuss few more properties of uniformly continuous function, and then we shall see few more examples. So let's recall the definition of uniformly continuous function. So this was the definition. So let f a to r be a function where A is any set in R, that is any non-empty subset of R. Okay. Now the function f is called uniformly continuous on the domain A if for every epsilon bigger than 0 there exists a delta bigger than 0 such that mod of x minus y less than delta and xy belongs to A implies mod of f of x minus f of y less than epsilon. Okay. So this is the definition of a uniformly continuous function on a domain A. Now from this definition we can say that a function f is not uniformly continuous on the domain A if and only if there exists a positive epsilon bigger than 0 such that for all delta bigger than 0 there exist 2 points, say x, y, in A with the property that mod of x minus y less than delta but mod of f of x minus f of y bigger equal to epsilon. Okay. So if f is a uniformly continuous function on the domain A, then that was the definition, right? And this was the negation of the previous definition. That's mean f is not uniformly continuous if and only if this condition holds. Fine. Now we prove one equivalent criteria of this continuity. Now we prove the theorem. The theorem says, so again let f a to r be a function, then f is uniformly continuous on A if and only if for any two sequences xn and yn in A with mod of xn minus yn converts to 0 as n tends to infinity. We have mod of f of xn minus f of yn converts to 0 as n tends to infinity. So here is the proof. So first let this condition as a star. So that means star means for any two sequences xn and yn in A with the property that mod of xn minus yn converts to 0, we have f of xn minus yn converts to 0. Fine. That's mean we have to prove that f is uniformly continuous if and only if the condition star holds. Okay. Now we assume that if possible the condition star does not hold. So that's mean there exist two sequences xn and yn in A such that mod of xn minus yn that converts to 0, but mod of f of xn minus f of yn that does not converts to 0. So we can write this is greater equal to some number epsilon for some epsilon bigger than 0. Okay, and this is true for all n. Why we can write that? See, a mod of f of xn minus yn that does not converge to 0, right? That's mean, since this is a positive number, so that's mean this sequence either diverges to infinity or it is a oscillating kind of sequence. Now if it diverges to infinity, that's mean after some stage all of this number will be bigger than equal to some positive real number. Okay, now if this sequence is an oscillating sequence, then we will have a subsequence of this oscillating sequence, say f of xrn minus f of yrn, okay, that converts to some number r that is bigger than 0. Therefore after some stage all of this number is bigger equal to some epsilon. Fine. Now what we will do in that case, we can consider that xrn and yrn as our main sequence. Then we will have two sequences, say xn, we can call it as xn and we can call it as yn. Then we will have two sequences, say xn and yn in A, such that mod of xn minus yn converts to 0, but mod of f of xn minus f of yn greater equal to epsilon. Okay, now if we choose this epsilon, then for this epsilon bigger than 0 there is no delta bigger than 0 such that xy in A with mod of x minus y less than delta will imply mod of f of x minus f of y less than epsilon. Why? Because for each delta bigger than 0 there exists a natural number n such that mod of xn minus yn less than delta for all n bigger equal to n. Why? Because the sequence mod of xn minus yn converts to 0, right? Now that imply mod of xn minus yn that is less than delta and mod of f of xn minus f of yn that is bigger equal to epsilon from this, right? So thus we have two numbers, two elements xn yn in A and mod of xn minus yn, that is less than delta, but mod of f of xn minus f of yn, that bigger equal to epsilon, right? This implies for this epsilon there is no delta such that this condition holds. That's mean f is not uniformly continuous on the domain A. So we assume that the condition star does not hold, and then we prove that f is not uniformly continuous on A. So thus, if f is uniformly continuous, then the condition star must hold. Now we prove the converse part. That's mean we assume that the condition star hold, and we prove that f is uniformly continuous on A. So first of all, assume that f is not uniformly continuous on the domain A. Then there exists epsilon bigger than 0 such that for all delta bigger than 0 there exist 2 points say x, y in A such that, or with x minus y, that is less than delta, but mod of f of x minus f of y greater equal to epsilon. Now take delta equal to 1 by n, right? Now for this delta there exist 2 points, so choose xn, yn in A such that mod of that number, say xn minus yn less than delta, that's mean less than 1 by n, right? And mod of f of xn minus f of yn, this is greater equal to epsilon, right? Since for each delta we have this, so therefore we choose two numbers xn, yn such that mod of xn minus yn less than 1 by n, but mod of f of xn minus f of yn greater equal to epsilon. Now then you can check that xn minus yn, that is converts to 0, but mod of f of xn minus f of yn, that does not converts to 0 as n tends to infinity. So this is a contradiction. So that implies the condition star does not hold. So we assume that f is not uniformly continuous on A, and we prove that the condition star does not hold. In other words, we have the condition star holds, imply f is uniformly continuous on the domain A, right? So we are done. Now it is easy to prove that if f and g are uniformly continuous functions on A, then f plus g and f minus g are also uniformly continuous on the domain A. The proof is very simple, and here is the proof. So let xn and yn be two arbitrary sequence in A such that mod of xn minus yn converts to 0 as n tends to infinity. Now since f and g both are continuous, both are uniformly continuous, on A, therefore f of xn minus f of yn, that is converts to 0, and g of xn minus g of yn, that is converts to 0 as n tends to infinity, right? Now therefore if you take f plus minus g, that xn minus f plus minus g did yn, you can write this is as f of xn minus f of yn plus minus g of xn minus g of yn, and this is less than equal to mod of f of xn minus f of yn plus g of xn minus g of yn. And since both terms converts to 0 as n tends to infinity, therefore that tends to 0 as n tends to infinity, right? Now since xn and yn are arbitrary sequences in A, therefore we can say that f plus minus g is uniformly continuous on the domain A. Now note that if f and g both are uniformly continuous on A, then f into g may not be uniformly continuous on the domain A. So here I write as a note. So if f and g both are uniformly continuous on the domain A, then the product fg may not be uniformly continuous on the domain A. For an example, you can take f of x equal to x, and also you can take g of x equal to x on R. We know that f of x equal to x, that identity functions are uniformly continuous on R, but f into g, which is fx equal to x square, is not uniformly continuous on R. So uniformly continuous on R, but if gx, which is x square, is not uniformly continuous on the domain R. Okay? There is another interesting property of uniformly continuous function, is that uniformly continuous function sends Cauchy sequence to Cauchy sequence. That's mean, so let f be a uniformly continuous function on the domain A, and let xn be a Cauchy sequence in A, then f of xn must be Cauchy, that is also a Cauchy sequence. Okay, so here is the proof. It is given that f is a uniformly continuous function on A, and it is given that xn is a Cauchy sequence in A. Okay, now we have to show that f of xn is a Cauchy sequence. First we choose some arbitrary epsilon bigger than 0. Okay, now since f is uniformly continuous, on the domain A, therefore for this epsilon there exists a delta bigger than 0 such that whenever x, y, two elements in A with the property that mod of x minus y less than delta, then that will imply f of x minus f of y less than epsilon. Okay, now it was also given that xn is a Cauchy sequence. Now since xn is a Cauchy sequence in A, therefore for this delta there exists a natural number n such that mod of xn minus xm less than delta for all n comma m bigger equal to n. Now note that for all n comma m bigger equal to this capital N, the terms xn and xm are in A and their difference is less than delta. Therefore, if we give this 1, then by 1 we have mod of f of xn minus f of xm less than epsilon for all n comma m bigger equal to n. That is, we have chosen that arbitrary epsilon bigger than 0, and for this epsilon we get a natural number n such that f of xn minus f of xm less than epsilon for all n comma m bigger equal to n. So thus the sequence f of xn is a Cauchy sequence. Now one can ask, what about the converse of this? That's mean if you have a continuous function which sends every Cauchy sequence to a Cauchy sequence, does it imply that the function is uniformly continuous? The answer is no. You can take f r to r such that f of x equal to x square. Then you can check that f sends any Cauchy sequence to a Cauchy sequence, but the function f is not uniformly continuous. The function is not uniformly continuous, we have seen that, right? Now we prove that the function sends every Cauchy sequence to a Cauchy sequence. In fact, we shall prove more stronger than this. So we prove that let f be any continuous function from R to R That's mean the domain of f is R itself. Now if f is a continuous function with domain R, then f always sends a Cauchy sequence to a Cauchy sequence. Why? So we use the completeness property of R. So first of all, let xn be a Cauchy sequence in R, right? Now if we take a Cauchy sequence in R, since R is complete, we can say that the xn is convergent and converges to a point in R. Now since R is complete, that's mean xn converges to a point in R. X in R. Now it is also given that f is continuous on the domain R. That's mean f is continuous at x as well. Now since f is continuous at x, therefore, or we can say, and xn converges to x, therefore f of xn converges to f of x. That implies f of xn is a convergent sequence in R. So we can write, since f of xn is a convergent sequence in R, so by the Cauchy's criteria, we know that the sequence f of xn is a Cauchy sequence. Now what will happen if we take the domain as a proper subset of R? Then can we say that f sends every Cauchy sequence to a Cauchy sequence? In that case, we cannot say that. For an example, if we take a function f from open interval 0, 1 to R defined by f of x equal to 1 by x, then obviously f is a continuous function, right? So then f is a continuous function. Now take xn equal to 1 by n. Now then the sequence xn is a Cauchy sequence, but the sequence f of xn, which is just n, is not a Cauchy sequence. That's mean if you take the domain is a proper subset of R, then f may not send a Cauchy sequence to a Cauchy sequence. That's mean here we can also say that the function f is not uniformly continuous, right? Because every uniformly continuous function, whatever the domain is, always sends a Cauchy sequence to a Cauchy sequence. So here we can write, thus we can say that f is not uniformly continuous. Okay, so these are all about the properties. Now we shall see few examples, and not only from the uniform continuity, we shall see the problems from continuity and uniform continuity as well. So let's start with this problem. So let f be a uniformly continuous function where the domain is open interval 0 infinity. Then what can you say about limit x tends to 0 plus f of x and limit x tends to infinity f of x? That's mean, what can you say about the right hand limit of f at x equal to 0, and what about the limit at infinity? Okay. Now first of all, so you can easily observe that if f is a uniformly continuous function on some open interval ab, then limit x tends to that a plus f of x and limit x tends to b minus f of x both exist, because so let xn be a sequence in open interval ab such that xn converts to a. Now that's mean, since xn is a convergent sequence, that's mean the sequence xn is a Cauchy sequence. Okay? Now that implies, since f is uniformly continuous on the interval ab, therefore f of xn, this is a Cauchy sequence in R, right? Now since R is complete, so every Cauchy sequence is convergent, therefore f of xn, the sequence this is convergent. So let f of xn converge to R. Since the sequence xn is an arbitrary sequence on the open interval ab and converges to a, therefore limit x tends to a plus f of x, that will be R. So thus the right hand limit exists. Limit x tends to a plus f of x exists. Therefore in this case we can say that limit x tends to 0 plus f of x exists. Now we claim that limit x tends to infinity f of x may not exist. So note that if we take f of x equal to x, then f is uniformly continuous on the open interval 0 infinity, right? And limit x tends to infinity f of x, it is infinity as well, right? In this case we can say that limit exists and it is unique. In fact, you can choose a function where the limit is a finite limit. Okay? But if we take f of x equal to say sin x on the open interval 0 infinity, then first we prove that f is uniformly continuous, and then we show that the limit as x tends to infinity does not exist. So why f is uniformly continuous on that domain? So let xn and yn be two arbitrary sequences in the domain 0 infinity such that say mod of xn minus yn that tends to 0. Now what about mod of f of xn minus f of yn? Now that is equal to mod of sin xn minus sin yn, and that is equal to 2 times sin xn minus yn by 2 and cos xn plus yn by 2. Now that is less than equal to 2 mod sin xn minus yn by 2. Okay. Now since xn minus yn that converts to 0 as n tends to infinity, that imply xn minus yn that is also converts to 0 as n tends to infinity, that imply sin xn minus yn by 2 that is also converts to 0 as n tends to infinity, right? And therefore mod of f of xn minus f of yn that is also converts to 0 as n tends to infinity. Now since the sequence is arbitrary, therefore f is uniformly continuous on the domain 0 infinity. Fine. Now we claim that limit x tends to infinity, f of x does not exist. Why? Because here fx equal to sin x. Now if we choose my xn equal to say 2n pi, or you can say 1 pi, then xn converts to infinity, but f of xn that is 0, so converts to 0 as n tends to infinity. Now if we choose yn equal to say 2n pi plus pi by 2, then again yn diverges to infinity, but f of yn that is just 1 and it is converts to 1 as n tends to infinity. That's mean whenever you have chosen two sequences, say xn and yn, both diverge to infinity, but f of xn one time it converts to 0 and for other case it converts to 1. So therefore limit x tends to infinity, f of x in this case does not exist. Now if you take f of x equal to say 1 by x plus 1 on the domain 0 infinity, then you can check that limit x tends to infinity, f of x that is 0, right? That is exist and finite. See, last time when we took fx equal to x, then the limit exists but was infinite, right? But in this case the limit exists and finite, and we claim that f is uniformly continuous on the domain 0 infinity. Why? First of all, take, or we can say let xn and yn be two arbitrary sequences in the domain 0 infinity, such that mod of xn minus yn that converts to 0. Now what can we say about mod of f of xn minus f of yn? Now see, that is 1 by xn plus 1 minus 1 by yn plus 1, right? So that is xn plus 1 yn plus 1, and that will be yn minus xn. Now since xn plus 1 is bigger than 1, therefore 1 by xn plus 1 that is less than 1. So you can write it is less than mod of xn minus yn, right? Now this converts to 0 as n tends to infinity. So thus f of xn minus f of yn that converts to 0 as n tends to infinity. So thus f is uniformly continuous on the domain 0 infinity, right? So therefore we have chosen three functions, and for one all of three are uniformly continuous on the domain, but for one we had limit infinity, for one we had limit does not exist, and for this we have limit exists and it is finite, right? So therefore we can say that in our case, so limit x tends to infinity, f of x may not exist, right? Now note that here during this proof I used one important result of uniform continuity, and here I state this. So let f be a continuous function on the domain open interval ab, then f is uniformly continuous if and only if the right hand limit at x equal to a and the left hand limit at x equal to b of the function f both exist. Why? Now if the both limit exist, then we can extend this function continuously on the domain closed interval ab. Now we know that any continuous function on closed and bounded interval is uniformly continuous. Therefore f is uniformly continuous on the domain closed interval ab. Now since the open interval ab is a subset of the closed interval ab, therefore we can say that f is uniformly continuous on the open interval ab as well. Now conversely, if f is uniformly continuous on the open interval ab, then during this proof I proved that the right hand limit at x equal to a and the left hand limit at x equal to b both exist. So we are done. Now consider the following problem. So let f be a continuous function from closed 0 open infinity to closed 0 open infinity. Then is it true that f must have a fixed point? That means there exists a point x0 such that f of x0 equal to x0. And the second problem is, so if there is a point m such that f of x less than equal to m for all x, then can we say that f has a fixed point? Okay, so we shall ask this problem. So here is the solution. So first of all, the part 1 is not true, because if we take say f of x equal to x plus 1 on the domain that close 0 open infinity, then f is continuous, but does not have any fixed point. Right? So part 1, that is not true. Now what about this part 2? Now that is true. Why? Because note that since f of x less than equal to m for all x belongs to 0 infinity, so we can consider the function as so f from close 0 open infinity to close 0 open m. Now since this f is continuous, therefore the restriction function of f, say f restricted over 0m from 0m to 0m is also continuous. Right? Now we know that if we have a continuous function from the same closed interval AB to the same closed interval AB, therefore it must have a fixed point, and that theorem is called the fixed point theorem, right? So therefore, by the fixed point theorem, so there is x0 belongs to the closed interval 0m such that f of that x0 equal to x0. So thus you can say that f has a fixed point. So we are done. Now we can see another example. So say problem 3. Now let f of x equal to x to the power n plus a n minus 1, x to the power n minus 1 plus a1x plus a0, where that a0, a1 up to a n minus 1 belongs to R and n is odd. Now then prove that f has a real root. That's mean we have to prove that there exists a number say c such that f of c equal to 0. Fine. Now here we use the intermediate value theorem. Actually we will find a large n such that f of n is bigger than 0 and f of minus n is less than 0. And then we can show that, that is by the intermediate value theorem, we can show that there exists a root in minus n comma n. Okay, so this is the idea of the proof. So first of all, so here f R to R be a continuous function. Right? Because f is a polynomial function, so it is a continuous one, right? Now observe that limit mod x tends to infinity, that's mean either x tends to infinity or x tends to minus infinity, this term say a n minus 1 x plus a n minus 2 by x square a0 x to the power n. Now you can see that this is equal to 0, right? This is trivial. Now since the limit of this term, this function is tends to 0, that's mean we can choose a large number such that, or you can write here, so thus for large n, so bigger than 0, we have say minus half less than equal to this one, a n minus 1 x, a n minus 2 x square plus a0 x to the power n is less than equal to half for all, or you can mod x bigger equal to n. Since mod x tends to infinity implies that this function tends to 0, therefore we have large n such that whenever mod x greater equal to that n, then this function will be lie between minus half and plus half. Now we can add 1 on the both sides, so we will have 1 minus half less than equal to 1 plus a n minus 1 x plus a n minus 2 x square a0 x n less than equal to 1 plus half. right? Now we can write it is as half less than equal to this one, say 1 by x to the power n, say x to the power n plus x to the power n minus 1, or you can write a n minus 1 x to the power n minus 1 plus a0 less than equal to 3 by 2, or we can write half less than equal to 1 by x to the power n f of x less than equal to 3 by 2, right? And this is true for all mod x bigger equal to n. Now if x is bigger equal to n, then x is positive, right? So we have half, or you can say x to the power n by 2 less than equal to fx less than equal to 3 by 2 x to the power n. And if x is less than equal to minus n, that's mean if x is negative, then that will be, you can write now 3 by 2 x to the power n less than equal to f of x less than equal to x to the power n by 2, right? Now this implies f of capital N is bigger equal to, you can check here, n to the power n by 2, that is bigger than 0, and f of minus n, that is less than equal to, you can check, minus n to the power n by 2, right? So minus n to the power n by 2, that is equal to, since n is odd, so that will be minus n to the power n by 2 less than 0. Thus, by the intermediate value theorem, we can say that f has a root in the interval minus n comma n, right? So we can say that f has at least one real root if n is odd. So we are done.